Okay, so let's just go over a few of the concepts that we covered before we go on to the neural network chapter, before we go on to chapter 11. So let's review what we meant by the gradient, and let's make it a little bit clearer. So we're going to talk about the gradient of a scalar valued function. So remember, what does that mean? So a scalar valued function would mean that it's a function from, let's just ignore this. It's a function from Rn to R. So we can have many inputs, but we only have a single output. So we're allowing many inputs, but we're only considering the case where we have one output. So we can call it scalar valued as opposed to vector valued. So then the gradient is the set of partial derivatives. And here we're writing it as a vector. So we have the partial derivative of, so our function is called f, and we're using this symbol for the gradient. By the way, this is read as nabla. This symbol is read as nabla, but we'll just call it the gradient of the value of the function f. And as we said, we're allowing x to be a vector. In other words, the input isn't just a single value. It could be a vector. But the output, this is not bold, so the output is not a vector. It's just a scalar. That's the case we're considering here. And then the gradient is basically the set of partial derivatives. So remember, this x has like an x1, an x2, an x3, up to an xn. And we're going to take the partial derivative of this with respect to x1, the partial derivative of this with respect to x2, and so on, all the way until we get to the end, the partial derivative of f with respect to xn. We put all those together in a vector, and we call that the gradient. Now, we haven't mentioned it yet, but we can also use this notation, and basically we have the same thing in here. This just means exactly the same thing right here. This means the partial derivative of f with respect to x1. This means the partial derivative of f with respect to x2. So these mean exactly the same, but here we are putting in the value of a. Here we didn't put in any particular value, so the gradient doesn't refer to a particular point. It's just the operator. This is just the operator, just in the same way that we might say this symbol, this orange here, is the derivative of f with respect to x, but that's not at a particular point. That's just the general formula for the derivative. So, for example, if we had this function y equals x squared, we would say the derivative of that is 2x, but we're not specifying a particular point yet. I mean, we can specify a particular point by putting in a particular x, but right here, we're just saying that's the formula. So this is considered kind of an operator. So this is the same kind of thing, but in multi-dimensions. So we're not specifying a particular point here. We can specify a particular point, but right here, we're not doing that. And then what we mean by this is this, first of all, it's not a vector anymore. It's a matrix. You can see it has these hard brackets. And as I said before, this just means exactly the same thing as this. But now we're putting in a particular a. So we're putting in a particular point. It's like we put in a particular, we'd say, we often would write something like this: when x equals 5, and then we'd have to do this when x equals 5. But the final answer would be 2 times that 5, or 10. So we'd have to put that 5 in there. So that's what we're doing here. We're putting, so this is like when x equals 5, evaluated when x equals 5, but this is not just a a single scalar. This is a whole vector, so evaluate it at a particular vector. And that means we take the partial derivative, but we put a into it, just like we put 5 into here. And we put we put a into here, and all of them. So that's what this means. This means we'll say that's the derivative of this same function at a, and it's very close to the gradient, but the gradient is just this part. But when we talk about the derivative, we talk about the derivative at a point, at a particular point. Now this is a point in Rn, so it's a vector. But anyway, I'll call it a point. The derivative at a particular point, and so we have to put in the actual point into each of the partial derivatives. So and then we put the square brackets around this, and that is a matrix now. And so we say it's the row matrix whose entries are the components of this. So this is the nabla operator, or the gradient of f at a particular value. So here, when we write it like this, we're not specifying a particular value. We're just being general, a general x. So let's just do an example of this. Let's take an n-dimensional paraboloid. So a paraboloid comes from parabola, and the typical formula for parabola, or the simplest formula for parabola would be this one. So now if we have two input variables, then we'd have this plus the second one would also be squared in order for it to be called a paraboloid. And then if we wanted to continue with more than just two input variables, we could keep going. And as long as we follow this pattern, we're still going to call it a paraboloid. We're going to call it an n-dimensional paraboloid. So this would be called a one. I guess in this terminology, this would be called. This is a little bit different than the terminology we use, because this would be called a two-dimensional paraboloid, and this would be called and then if we had both of them, this would be called this would be called a one-dimensional paraboloid, and then if we had these two, we'd call that a two-dimensional paraboloid. So I think I was calling this a three-dimensional paraboloid. But anyway, here we're calling it a two-dimensional paraboloid. So we're just referring to the number of inputs when we say two. And then, but how many dimensions is this whole thing? Do we need to graph this whole thing? We need 3 dimensions. And how many dimensions do we need in general to graph a so-called n-dimensional paraboloid? We need actually n plus 1. Just like here, when we had 2, we needed 3 dimensions. Just like here, when we have n, we need n plus 1 dimensions. So this is kind of taking the place of the y here. So the y is one more dimension, so it's x to the n plus 1, we could also call it. So now with this example, let's generate this thing. So what is this thing? It's just the partials of the function with respect to each one of these, x1, x2, and so on. So this is the function we're working with. And the partial of f with respect to x1, so everything else is constant, we get 2x1. The partial of f with respect to x2, everything else is constant, so we get 2x2. And in general, the partial of f with respect to xi is 2xi for any of the i's. So now, if we want to say for this particular example, what this will be, it's the partials that we just mentioned over here, and we fill them in here. So we get the gradient of this is 2x1, 2x2, and all the way up to 2xn. Now if we want to evaluate this at a particular point, that means at a particular x1 is a particular value, x2 is a particular value, and so on. So it's a particular point in space. This is an n space, but anyway, a particular point in space. Then we have to put in those values to find out the derivative. Just like when I wanted to know what's the derivative when x equals 5, I first calculate the derivative, and then I put in x equals 5, and I get 10. So I have to do the same thing here. So first I calculate the gradient, and then I put in the values. So they're saying at the point 1, 2, 3, da, 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 da. So it's kind of just an arbitrary point that they've indicated here. So we have to put in 1 for this, 2 for this, and all the way up to n for that. So if we do that, we get 2 times 1, 2 times 2, and all the way up to 2 times n. So this is what the gradient, which is kind of like the slope, would be in this scenario. So at this point in n space, what will the slope be? And this would tell us. Now, if we wanted to use the derivative notation or the matrix notation, that is this notation, this notation here, if we wanted to use that notation, so that we want this thing, and it's a matrix, we mean we do the partial and put in the value there. So we're going to get exactly the same thing, but we have this notation now, and the only difference is that we have this here and here, whereas we had this here and here. So the gradient evaluated at a particular point is this vector. The derivative evaluated at this particular point is this matrix. So basically, if we want to use a vector, we'll call it the gradient. And if we want to use the matrix form, we'll call it the derivative. So let's go back to our chain rule, and we can do it in matrix form and in vector form. So we said just a little while ago, just in the previous video, that we can talk about the chain rule. Remember, what's the chain rule asking? We have the scenario where f is a function of many variables, and then this x, which is the many variables, each of those individually is a function of t. So that's the scenario we were talking about when we discussed the chain rule. And we wanted to know the partial derivative of f, not with respect to these intermediate variables like x1, x2, xn, but with respect to the t inside each of them. So we wanted to know the derivative of f with respect to t. Now in this formulation here, we're doing it at a particular point t, but let's just ignore that for now. So what did we say? We said that we would get the partial derivatives with respect to x1, x2, and xn, and then we could just matrix multiply that times this, which was the derivative of this is the full derivative of x1 with respect to t, the full derivative of x2 with respect to t, and so on. And we saw that if we did the matrix multiplication of this and this, we would get this times this, this times this, this times this, and so on. And that was exactly what we wanted. That gave us the chain rule. So we can say the chain rule can be expressed in two ways here, because we can think of this as a matrix, which is what I said it was just now, or we can think of it as a vector. So if we think of it as a matrix, so we're multiplying this matrix, this row matrix, times this column matrix, then we would call this, as we just said earlier, we would call this the derivative of f because we're thinking of it as a matrix. And then this thing would be called the derivative of x. So this is the derivative of x. And so we could say, if we want to call it, so as I said in the last video, we said we could just multiply this by this, and that would give us the whole chain rule. And so that's a kind of very elegant expression of the chain rule. And if we call this, and if we call this green, then we get this expression of the chain rule. And if we think of this rather, instead of as a matrix, as a vector, so then we're talking about this notation, the gradient of f, and we think of this as also a vector, the derivative of x with respect to t0. So we have to talk about the derivative of each component of x. Then we would say it's this thing times this thing, but then it's not matrix multiplication anymore. It's the dot product. The dot product would give us that. So here we have it expressed as a dot product of this vector and this vector, or here we have the same thing expressed as matrix multiplication of this matrix times this matrix. So that is a view, two views of the chain rule. One is in matrix form and one is in vector form. Okay, so let's start on chapter 11. So we've covered the mathematics in chapters 9 and 10, and now we're ready to use the math in pursuit of our neural network. So we're going to talk about something called a neural network, and a simple picture of a neural network would be this. We have what's called 3 nodes here, or 3 circles. We call them nodes, and they're coming in layers. So we'll call this the first layer, the second layer, and the third layer. And then here we have a slightly more advanced version of that, where the first layer can have 2 nodes, and then these 2 look the same as these 2. And then we have even a more advanced version of it. So the first layer has 2 nodes, the second layer has 3 nodes, and then the last layer just has 1 node. So we're going to consider each of these in turn, and we're going to sort of start with this one and see what we mean, and then we can generalize it a little bit more and do this, and then we'll generalize it a little bit more and do this. So we've talked before in the previous chapters about data science and machine learning, and we worked through a couple of different algorithms. The last one was the naive Bayes algorithm. And anyway, in all 3 of them, we took a new example and tried to predict its class. And we're doing the same thing here. We're just doing it a different way. So we want to sort of train the model first and then use it. And what we mean by use it is give it a new example and ask it to predict the class. Now, we've been doing everything so far in terms of predicting a class instead of predicting a number. And we're going to continue with that here. We're going to predict a number. So some of the terminology here is that, as we said, this is called a node, a node, a node. And this is called the first layer, or this is called the first layer, or this is called the first layer. This is called the second layer. This could still be called the second layer. And this is called the third layer. We also say this is the input layer, and this is the output layer. Now, in neural networks, we could have more than one hidden layer. So here we just have one hidden layer. Here we still have just one hidden layer. We could have several hidden layers. So we could have maybe 3 here, and then 10 here, and then 5 next ones, and then so on. And then you'd have the last layer would still be called the output layer. It may not be the third layer, but it would still be called the output layer. And then these lines here are sometimes called the edges, or sometimes they're called the connections. You might just call them the lines, and so on. Now the lines or the edges or the connections will be assigned like a W here, W1, a W2 here. Here we have a W1 sub 1 and a W1 sub 2, and this is still W sub 2. And here we have we have more W's here. So we need some way to label them, but we have more W's because we have more connections from here, from this layer to this layer, so we have more W's. Whatever way we want to label them, it's not really that important, but we need to have a W for each edge. Now you also might notice that here we have an x1 and an x2, and that means basically we have an example or an input that has two attributes. So going back to our example from a long time ago, we might have, this might be that they voted yes on issue 1, and they voted yes, or I'm sorry, this might be how they vote on issue 1, and this might be how they vote on issue 2. So we'd only have in this drawing, we'd only have be allowed to accept the first two votes. So not, I think there were actually 16 votes that we had in our data set, but here we could only accept 2. Or going back to the iris setosa, the iris flower example, this might be the petal length, and this might be the sepal length. So we'd only be able to accept 2 inputs in this picture, in this model. Of course, we could just have more nodes in here, and then we could accept more inputs. But anyway, in this picture, these stand for the inputs, and this stands for the output. So here we only have one output, so it could be a number, or maybe something else, but at least at the beginning, it's actually just going to be a number. So we're going to get a number out here. So we're going to take our input and do something with it. And then anyway, eventually we're going to, it's going to give us an output. And that output is going to be the predicted value, or maybe the predicted class. So this might work for the stock market. So then you'd be inputting some input about the stock market, and then you'd predict the price of the stock market, maybe for the next day or something like that. Now the way that this works is that we take, let's suppose that x is a number. So we take a number in here, and we don't do any kind of transformation here. So we just say, if we take x, we're going to output x. That's why we have 2 x's. So this is what we take in, and this is what we output. So in this node, we don't do anything to x. We just pass it straight through. But later on, we're going to do something in the middle. But here we just take x and we pass it straight through. Okay, now what do? We take this w. Now this w is going to be a number. This w is going to be a number. And we're going to multiply this x times this w. And then, and that is going to give us this value here. So we're going to take, so z is the value that comes in to this node from here. So that means we're taking this times this to get z. And this 2 means that this z is in the second layer. So, and then over here, okay, so to get this z2, all we do is take this x, which is a number, times this w, which is also a number. Okay, now in this case, to get this z2, when we have 2 inputs here, we have 2 w's here. These are weights, actually. They're called weights. So we have 2 weights here, and we're going to take x1 times this weight, and we're going to take x2 times this weight, and we're going to add those together to get this z. So in the case here, we have 2, and going to here, that's how we're going to get this value, z. So we're going to take, once again, we're going to take this number times this, and then this number times this, and add those 2 products together to get this. That's how we get z2 in that case. And in this case, how do we get this z1? So we're going to take this value of x times the weight that connects here, and this value of x, or this x2, times the weight that connects here. So this weight happens to be called W11, and let's see if we can figure out what this weight is. It's a little hard to see, and just by looking at the picture, but this one is called W21. So this is called, the weight on this line here is called W11, and this line here is called W21. So suppose that's true, then how do you calculate this? You take this value, this is going to be a number, times this number, this weight, plus this number times this weight. Okay, and that's how you get this. Now how do you get this one? So you take this value times the weight on this edge, which happens to be W12, and then you take this value times the weight on this edge, and you add those two together to get this, and then you can see you're going to do the same kind of thing for this number. So that's how you get the Z1, Z21, Z22, Z23. So again, you can see that the notation here is that in the parentheses up top here, this tells you the layer. So this is not squared, it has nothing to do with squared. It's just means the layer number where this is, and this is in layer number 2. So this is Z with a parentheses 2 up at the top. This is also 2 at the top. This is also 2 at the top. Now here, this is Z with a 3 at the top. So that means this is the Z in layer 3. So that's what these upper superscripts with parentheses around them mean in this notation. So let's see if we can summarize all of this using a little bit of mathematical notation. So what is Z2 in the first case in here? Z2 is just x times this. So let's see that here. So we have that Z2 is x W1. Now, I've used small case x and small case W1 in this case because really this is not, so this could be a matrix. We've said that sometimes capital letters will be matrices. So this could be a matrix, but in this, and actually in this case, capital W will be a matrix, but here we could call it a matrix, but since it only has one value in it, we could also just call it a number. So I'm doing that in the equation. So it's just this number times this number gives us this number, Z2, Z with the 2 at the top. So that's what we have here. This number times this number gives me Z2. Okay? And let's see, let's go down to the next, this one, and let's see what we have here. So we have, now we want this times this plus this times this gives me this. So how are we going to write that? So we can call x1 and x2 together. We can call it, this is a vector, and we can call these two weights together. We can call that another vector. So we can call that here, this vector. And then we want to do what? To get the Z2 here, what do we do? What did we say? We're going to take this times this plus this times this. Well, in terms of the two vectors, this is a vector x, and this is a vector w. And if we take the dot product of that x vector with the w vector, we're going to get exactly what we want. We want this times this plus this times this. That's the dot product here. So if this is the x and this is w1, and we take their dot product, we're going to get exactly what we want. So we can say that Z2 here is the dot product of this vector and this vector. So that's what we have here, the dot product of those two vectors. Now, we could also call them matrices. If we call this a matrix x1, x2, and we call W1 this matrix here. The dimensions of this are 1 by 2, and the dimensions of this are 2 by 1, and we can therefore multiply these two, x times this w, x times this w. That's going to give us a 1 by 2 times 2 by 1. That works. And that will give us z2, and that works just as well. So we could express it as a dot product or as a matrix product. And we're going to stick generally with the matrix product representation. Okay, and then we can do the same thing actually here. When we come down to this one, it's still going to work as long as we call this a matrix X, and then all of these, if we put them all together in a certain way, and there are 6 of them here because this connects to this, this, and this, so that's 3, and this connects to this, this, and this, so that's 3 more. So there are 6 weights here, and if we set them up right, and what do I mean by right? Like this. So we have, let's first of all, let's look at what the subscripts mean. How did we decide or how to label these? So let's take this one. W12 goes from here to here, but W12 goes from here to here. And how about W21? W21, here's W21. W21 goes from here to here. So once again, W12 goes from X1 to Z2. W21 goes from X2 to Z1. So the first subscript tells you where it's coming from in the layer to the left, and the second subscript tells you where it's going to in the layer to the right. So like this one is 2, 3. What does that mean? So it means that this 2 tells me where it's coming from in the layer to the left. So it's coming from here. And this 3 tells me where it's going to in the layer on the right. So it's going to layer 3. So that's how we've set up the subscripts. W23, W13, again, once more, W13, it's coming from, W13 must be coming from here, and it's going to here. So that is how we're labeling these weights. So now, if we set them up right, we want to be able to say that the matrix that contains these two, and then if we matrix multiply that with this weight matrix, which contains all of these, we want it to give us the output Z1, Z2, and Z3. So we want this to be either a 2 by 1 or a 1 by 2, I'm not sure yet. And we want this to be probably either a 2 by 3 or a 3 by 2, not sure yet. And we want the output to either be a 3 by 1, the z's, we're only concerned with the z's, or a 1 by 3. So let's see what we have here. So here's W. Here's the W. So 1, 1 goes here. 1, 2. Remember, the subscript on the left tells us where it's coming from. So there's only 2 places where it's coming from, either the first node in the X layer or the second node. So there can only be 2 first indices. So the first indices can either be like here, it's a 1, here's a 1, here's a 2. And those are the only possibilities. Either the first indice is a 1 or a 2, because that tells us where we're coming from, and we're only having 2 nodes here. We're only coming from 2 different possible places. So the first index can only be either a 1 or a 2. So let's see what we have here. So this is 1, 1, 1, 2, 1, 3. That means it comes from the X1 and goes to the second layer first node, second layer second node, second layer, third node, or it can come from the second x value, second x input, and go to either one of those three second layer nodes. So we have these 6 weights, and we've lined them up like this. So in terms of where they are in the matrix, the 2, 3 one is where? It's just where we would hope it would be. It's in the second row, third column. And the 1, 3 is in the first row, third column. Okay, so that's what W looks like. Now let's see what happens when we multiply these two matrices. First of all, are we allowed to multiply these two matrices? So this is a 2 by 1. I'm sorry, this is a 1 by 2, and this is a 2 by 3. So yes, we are allowed to multiply them. And now what happens when we do multiply them? Let's see, do we have a picture? Well, here it is. So we do this times this. Is that really what we want? And we multiply these two. Is that really what we want? Well, what do we really want? We want to figure out what this is going to be. It's going to be this times this. I'm sorry, this times this, and this times that. Is that what we get? I think so. We get x1 times that and x2 times that, and it worked. That gives us, that's what we wanted for this z1. Now, what's the output, by the way? What's the dimensions of the output of this? This, again, is 1 by 2 and 2 by 3. So the output is going to be 1 by 3, which is what we want. We want a 1 by 3. Well, you could say we want a 3 by 1, but it doesn't matter. We want to call it a 1 by 3 or a 3 by 1, as long as we get a value for z1, a z2, and a z3. So this will give us that, and it gives us exactly what we wanted. So you can check and verify, or you should read through here to make sure that you agree that when we do this x times w1, we're going to get the right size for the result, and each of the elements in the result is going to give us exactly what we wanted. And again, what we want is this times this plus this times this to give us this one, and so on. So you should check to make sure that all of these work by reading through the text. Okay, so now we've talked about how to go from here through these weights to get these values. Now the next thing we do is we need to talk about how we go from here to here, or here to here, or here to here. What is this? What is this A1? Where does that come from? Same thing in the simpler picture. Here, where does this A2 come from? We didn't explain that yet. And the same thing in the simplest picture. Where does this A2 come from? We talked about where this comes from. We talked about where this comes from, and so on. But we haven't explained this. So in order to get from here to here, what we do is we take this value, z2, and we put it into a function. And we don't. So anyway, what function are we going to put it into? So here in the first example, we say that we're going to put z2 into some function, where f is either the sigmoid function, which we talked about earlier, or some other function, okay, which in any case we might call f a threshold function, or sometimes it might be called an activation function. So either way, we're going to put it into some function. So let's say that we're going to put it into the sigmoid function. It doesn't have to be a sigmoid function. It could be other, there are several other functions we might put it into. But the key thing is that remember that the sigmoid function, remember, was an S-curve. It is not a linear function. So that's the one thing that we want to avoid. So it can be all kinds of other functions. Typically, though, it is like the sigmoid function or just one of a few others, but it doesn't have to be that. But the only thing that it really should not be is it should not be a linear function. That won't really do us any good. So let's suppose, though, that we're going to put it into a sigmoid function. So we're going to take whatever we got as the input, in other words, the z value. So these z values, or this z value, or this z value, and any one of them, we're going to put that into the sigmoid function, and that's going to give us an output. So if we put this into the sigmoid function, we'll get an output, and we're going to label it this. And if we put this into the sigmoid function, we'll get an output, and we'll label it this. And if we put this into the sigmoid function, we'll get an output, and we'll label it this. So anyway, we're going to put it into the sigmoid function. So z is going to go into the sigmoid function. So this f could be the sigmoid function. Okay? And now we know what these are. This, or just this one, or just this one. It's just taking this value and putting it into the sigmoid function to get this. This value, same thing. Or this value here to get the sigmoid, this value here to get that. Sorry, put this value, put it into the sigmoid to get this. This value, put it in the sigmoid to get this, and so on. So that's what the A's are. Now, what do we do with the A's? So here, now we get this A. What do we do? Well, this has a weight on it. We labeled it with this. And we're just going to take this and multiply it times this, just like we did. We took this and multiplied it by this. And we're going to take this. This is the output for this node. We say this is the input into the node. This is the output out of the node. And we're just going to multiply that output times this weight. And that's going to give us this. And then we're going to do the same thing again. We're going to take this and put it into a sigmoid function, and we're going to get something out, which we're going to label y hat. Same thing here. We'll take this, put it into sigmoid, get this, multiply this times this, get this, then put this into this a sigmoid function like this, and we'll label that output as y hat. And we can do the same thing here. Take this, put it in sigmoid, get this, sigmoid this, then take these, this one times this one times that, this one times that, sum them up, we get this z1 in the third layer, put that value into the sigmoid function, and get this. So here we use two different labeling systems. So here we have y hat, that's the output, y hat, that's the output, but here we're calling it A3. So you can see why we would call it A3, because we called this one A2. So we might call this one A3 coming out. A2 is coming out of this node, so A3 would be coming out of this node. But we can also use this notation y hat and say that it's the predicted value. That's what y hat usually means in statistics. It means the predicted value. We could label it as A13, or let's just say A3 up here, or we could label it as y hat. So let's see this a little bit more in action. So again, this is for the simplest one, so this picture here. So what are we doing? We're taking the x input, there's only one input, multiplying it times the only weight there. We get z2. We're taking that z2 and putting it into the sigmoid function. We're getting A2. Then we take that A2 and multiply it times the weight on the next edge, and that will give us Z3. Then we're taking that Z3 and putting it into the sigmoid function. We can call that either A3 or we can call that y hat. And then we can write that, well, what was Z3? Z3 was this, and what was A2? A2 was this. So instead of A2, I could write f of Z2 here. So I have f of Z2 W2. And I'm sorry, and then what was Z2? It was this. So if you just put all of these into here, replace everything, you end up with this. So you can just check that. So y hat is equal to this, but we can say what this is, and we just replace everything. These two we squish back in, and I guess this one we squish back into here, and we get this as the expression. So we can say that y hat is f of x w layer 1 times w layer 2, then put that into f. And so that's what y hat is. So we can write it like this as well. So y hat, or A3, is the predicted value. So what are we saying? What do we mean when we say it's the predicted value? Well, we have an input here. So it might be the petal length and the petal width of a flower. And then we get an output. Now, it's not a class. It's a number. So let's take a different example. Let's say this is something about a company and something else about a company, and we put those in, and we get a predicted price here. We get a predicted price for the stock for the next day. So we have some input, some information about the stock, and we get a numeric output, which might be the price of the stock tomorrow. Okay, so we could call it y hat is the predicted value, or we could call it also A3. But either y hat or A3. And so that is basically the neural network output. That is the prediction that we get from a given input. But of course, probably the prediction is not that accurate. And so we want to somehow learn from the error. But in order to learn from the error, first we have to define what we mean by the error. And the error is basically simple enough. We just mean the actual value, the actual price tomorrow, which presumably we can get tomorrow, versus our predicted price. So this stands for the actual price tomorrow, and this stands for our predicted price. And so we can just subtract the two, and we'll get our error. Now, it's very common to get rid of the positive versus negative sign in the measurement of the error. So, and that's because we want to be able to sum up the errors. And if sometimes we get positive errors and sometimes we get negative errors, it's very likely that we could sum up the error and get 0, but that's not really a representation of the fact that we got some kind of error. If we're always getting 0 for our error, the sum of our errors, that's somehow not a very accurate picture of what we're doing. So that cancellation is kind of detracting from our measurement of the error. So somehow we want to get rid of the cancellation, get rid of the plus minus cancellation. And so we could just take the absolute value of the error, then we would never get negatives and we wouldn't get cancellation. But instead of doing that, we choose to square. That's an alternative way to get rid of the error. Sorry, to get rid of the cancellation. And you probably recall from junior high school or high school that working with the absolute value in equations is pretty much trouble. So that's one good reason why we wouldn't want to do it with the absolute values sign. Working with squares is not nearly as much trouble as working with absolute value signs. So we're going to choose to square the error, although you could choose to take the absolute value. And then basically we want to compare, the error at one point to the error of another. And so it doesn't really matter if we multiply the error by a half or not, as long as when we're comparing, we multiply both the two parts that we're trying to compare, both by a half, then it doesn't really matter. So we're going to multiply this by a half, and that's because when we're working with this error in our calculations, we're actually going to be taking the derivative of the error with respect to, with respect to y. No, sorry, with respect to y hat, I think it is. And but anyway, then you have to use the chain rule. And actually, when you use the chain rule, you get 2 times something. And so if we have 2 times something and that something has a half in it, then we get the cancellation of 2 and a half. which just kind of makes things look cleaner. So we just throw in that extra half there. It doesn't matter. You don't have to do that either, but it just makes things look better when we end up working with this formula and we have to take its derivative. And so we have now our formula for the error here, and we call it J. Now, that's just, some books call it J, other books call it the error, and so on. But and other books call it the loss function. But anyway, we're just going to call it J for now. So now look at, we said that y hat was equal to A3, but we could also sort of push it all the way down to this level. And we get that y hat is equal to all of this. And so here, instead of y hat, we could just put all of that in here, and it's still the same equation. It looks like I forgot the square here, so that's an error in the book. Yes, unfortunately, there's a square here. Should be a square here that's missing. Now, once we have the error, then we might be able to so-called learn from it. I guess, we say we try to learn from our errors, and that's exactly what we try to do in a neural network. We try to learn from the error. And by the way, J is called the cost function. So the question is, how can we learn from the error? What can we do? Somehow, what does it mean to learn in this case? Or what does it mean? How could we improve our prediction? Because we're saying that we're not always going to get a perfect prediction. In fact, we actually never expect to get a perfect prediction of, for example, the price. We never actually expect to be able to predict the price exactly, or it seems unlikely. So how can we improve our price predictions? And specifically, we're talking about how can we change the network to improve our predictions. So here's the so-called network. This whole thing is called the neural network. So how could we change it to get better predictions? Well, we can't change this part here, x1 and x2. That's talking about the data we're getting. We don't change that. We get a new piece of data, we put it in. We get a new piece of data, we put it in. We don't change that. And then remember that Z1, Z2, and Z3, those are already determined once we get our input and once we have these weights. So we can't really change Z1, Z2, and Z3 just by hand. So, and the same thing with A2. A2 comes from Z1, and then Z3 comes from these and these. So if you look at this, you see that the only thing we can change here are the W's. So the W's are in this network. So this network is pretty simple, really. It only has, sort of inputs and weights. And that's all it is a bunch of inputs and weights. That's pretty simple. It's hard to believe that it could actually really accomplish anything. It's hard to believe that it could accomplish anything like being able to translate one language into another, or that it could figure out how you could use it to drive a car without someone being at the steering wheel, or all the other things that can be done in deep learning. But that's the whole thing. It's just these weights really, and what they should be. And as we said, we want to learn from the error, and all that's going to mean is that we're going to somehow figure out some way to adjust these weights so that we get a better prediction. Now, I didn't mention it yet, but you might have asked, well, where do these weights come from originally anyway? I mean, we said, suppose we have some weights here and we multiply them and so on, but we didn't talk about where we get the weights from initially. And the truth of the matter is, we just sort of choose them randomly. So the initial assignment of weights to each of these edges is just random numbers. Usually we keep the numbers between 0 and 1, but they're still random within there. So that's because we sort of don't know what else to do. We don't have there's no particular place to start. So we just select them randomly, And if you want to think about it, that's kind of like, you might think of like a baby is born sort of with just random weights, and then they in their neurons, but they learn and they change the weights, they improve the weights. Anyway, the point is that we have these weights and they're randomly selected at first. Then we get an output, we're going to get an error, and then somehow we're trying to figure out what to do to improve. In other words, how to take the error and and change things so that we get less of an error. So like we might say, well, if the error is really big, then probably we should change these weights by a lot. Because if we just change these weights by a little, we're not going to get much of a difference in our prediction. The error is still going to be big. So we might want to change the weights by a lot if the error is really big. But that's a pretty vague statement, just to say that. Just change by a lot is not exactly clear instructions about how to change the weights. So this is really the problem that the original scientists who were working on neural networks in the 50s and 60s of the 20th century were faced with. They had no idea how to change the weights in any kind of systematic way to improve the prediction. And it's not exactly clear what you should do. If you think about it, what could you possibly do? I mean, not such an easy problem to solve. So the first attempts, when they had a fairly limited network, like maybe this was the most complicated network they would work with, or maybe this was the most complicated network that they would work with. So in that case, you could sort of play with the weights. In this case, you only have 3 weights to play with, so that's not so impossible to change them in different ways and see what happens. Can you get a better prediction? But it doesn't seem all that scientific, it doesn't seem all that methodical, but you could do that, and you could keep, then you could run your data through again and see how well you did, and then maybe change it again, and maybe you'll come up with better predictions just by kind of doing it at random, or just maybe with some kind of intuition even. However, thanks to the great work of many mathematicians, not just recently, but mathematicians in the 18th century and the 19th century, and even probably before that, we developed the concepts of gradient descent and the calculus that we've just been studying. And the scientists in the 60s, 70s, and 80s of the 20th century built on their work. So we may say something like, or somebody said something like, well, the change, that is the reduction in the error, is related to a change in the weights. Well, that's obviously true, that the error is definitely related to the weights, and the change in the error, the reduction in the error, should be related in some way to the weights. Now that seems true, but it doesn't seem like something you would necessarily focus on. But some of these people, who I guess we can attribute some level of genius to, recognized that this statement has a lot of power. So this simple observation in the hands of the right mathematician may lead to a terrific development. And some mathematician may notice that this is suggesting that we may want to know what change we will obtain in J, in the error, if we change the weight W. And thus a mathematician may translate this question into this: what is dJ dW? Now, once it gets translated into this opens the door to all the great machinery that we have learned. So going from the problem of just saying, I want to reduce the error, or even using that word is kind of leading somewhere, so I'm not sure that, but anyway, saying I want to reduce the error how can I reduce the error, and saying, well, it depends on W, but then going to this opens the door to all the great machinery that we've learned, and that is, it opens to the door to the chain rule and to gradient descent. So once we sort of translate this problem of how can we improve our predictions to how can we change the error as a function of the weights to what is the derivative of the cost with respect to changes in W. Once we go there, then we're kind of on the way to something very powerful. And this is going to be the key to get to not just arbitrarily changing the weights and seeing how the cost reduces, but to some kind of methodical way to change the weights so that the error gets smaller. And we've sort of turned that question into a focus on this derivative. Now, we can say that easily in just, this one, 3 or 4 sentences here, but getting that insight, when you don't know which direction to go at the beginning, is not easy. We can rehash it now, and it seems like, oh, that's not so difficult to understand, but to develop it on your own is another story. So let's return to the text, and we're all the way down on page 244 here, and we have J, which we said was this, but we said that Y hat can be rewritten in terms of the W's and the inputs and so on, and we had this expression, which unfortunately, again, is missing the square here. How unfortunate that is. So anyway, there should be a square here, and then here we have the sort of fully expanded version, but here we're leaving A2 unexpanded, so then this looks a little bit simpler, and here I didn't forget to put in the square there. So anyway, this is J written out this way, and we can see that it depends on W2, which is what we certainly would expect, that the error depends on W2 in terms of the diagram. If we look at the diagram, of course, the prediction, our predicted value, is going to depend on W2, so our error is also going to depend on W2. So that's what we have here, that the error is dependent, or the prediction, this is the prediction, sorry, the error is dependent on W2. Now, we just said that we want to consider the derivative of J with respect to the weight. So first thing we're going to consider is the derivative of J with respect to the weight W2. Now, we're talking about the simplest network. That is, we have one node here, one node here, and one node here. Now, I included an extra circle just to say that we also want to calculate the error, but that's not exactly part of the network. But we can represent it as a circle with the error in it, because it does come from here. So once we get this, we can figure out the error. But anyway, we just have one node in this layer, one node in this layer, and one node in this layer. So what we're asking for is, like we said we wanted, dj dw. Now, which w do we want to consider? So we could consider this one, or we could consider this one. Well, this is the one that's closest to the error, so let's do that first. Let's consider dj with respect to W2, so that's what we have written here. dj with, sorry, not there. dj with respect to, well, here we have j as a function of W2, so we might be able to calculate dj dW2, this W2. In fact, we should be able to calculate. Now, though, in order to do that, you're going to have to use the chain rule here, and then you're going to have to do it sort of again and again and again, because this is sort of embedded in several different layers of functions. So we have a squaring function, and then it's also embedded in this f. So we'd have to use the chain rule again. And we didn't spend that much time on the chain rule, so I sort of assumed that you've used the chain rule, but maybe we should just do one quick example where this kind of situation would arise. So let's consider 3 different examples, and the last 2 need the chain rule, and this one needs the chain rule once, and this one needs the chain rule twice, and you could continue where you would need the chain rule 3 times and 4 times and so on, and we actually run into that when we're doing the neural network. But anyway, let's just do this. So first of all, suppose we have the function sine of x. Now this is not part of what we need in our class, so maybe you don't know the derivative of the sine of x, but the derivative of the sine of x is the cosine of x. So let me just write that down. So we have the derivative of sine of x is equal to cosine of x. Okay, now here in the second example, we're going to need the chain rule, because we'll think of it like this. So we can call g of x equal to the sine of x, and then we can call u of x equal to x squared, the inner function. So f is g of u of x. So that means we have the composition of g and u, and that's the function f. So we want the derivative of f means we want the derivative of a composition, and so we're going to need the chain rule. And we could write it like this. We want, I shouldn't say equal, sorry. We want d of f is equal to, by the chain rule, d of f with respect to u du times, now you may not be that fluid with this stuff, but I'm not going to spend too much time going through it. Anyway, du dx. So that would be the chain rule when we want this. The change in f with respect to a change in x. So x is the inner variable, but first we square it and then we take the sign. So we have the composition. So we need this chain rule. Now here, we have an outer function, then we have a squaring function, then we have another function inside that. So this is actually, let me rewrite this. So let's say this g is the sine function, that's the outermost function. U is the squaring function, which is here. And then p, we'll give another function. P is 3x minus 8, and that's the inner function. The third function is here. So we can say that f of x is g of u of p. So now the chain rule, now I'm not going to work through this, but now the chain rule is going to be, so if we want df dx, where f is the outside and x is in here, we have to go through sort of a chain. We have to do df du, so that means like u is this whole thing here, and then du dp, and then dp dx. So that is the chain rule when we have one function, this function here embedded in another function, which is embedded in the squaring function, and then that is embedded in the sine function. So in that case, we need this kind of chain rule with 3 parts. And actually with ours, we're going to need 5 levels, because our network has several different processes and things are embedded in other things. And then actually when we do another time, we're going to actually need 7 of these to get our derivative. So anyway, that's just using the chain rule. And you might want to go back and review and get some practice in that. So going back to here, you can see that if I want dj, dw2, that is this thing here, this w2 is embedded in this f, and then that is in here, and then we're squaring it. So there's several different processes involved, and so the chain rule is going to have several factors. And so if I call Z3, remember Z3 is the output here, sorry, Z3 is here, and then Y hat is F of Z3. We put Z3 into the sigmoid function, we get Y hat. So anyway, if we call Z3 this, Y hat is F of Z3, and then the error, or E rather, is Y minus Y hat, and then we're going to square the error, we'll call that S, and then we're going to take 1/2 of S, and we're going to call that J. So J is 1/2 S, but S is E squared, so we have 1/2 E squared, but E is Y minus Y hat, so we get 1/2 Y minus Y hat squared, but then Y hat is this, so we get 1/2 this to that, and then we get all this. So if we want dw2, as I said, we're going to get a kind of a long string, and you can work with this, make sure you understand it and agree with it, but you can sort of see that, the mnemonic is that, well, this S cancels with this E cancels with this cancels with that cancels with, but that's not really fair just to do that. You have to really understand that this is the chain rule. Okay, so you should understand that. You should make sure that you can do that. And so anyway, we get this result here. And this tells us the way that when we change W, the corresponding amount that J will change by, or it tells us, or it gives us an expression for how a change in W2 here, will provide a change in J. And that's what we wanted to do, or that's sort of on the way to what we want to do. We want to know how much our changes in W are going to change J, and that's going to somehow lead us to know how much to change the weights by in order to get a corresponding improvement in J. If we do it now, you may say, well, what do you mean by the right way? How much should we change W by to bring about a reduction in J? But actually, haven't we already discussed this? Remember that J is a function of W, and this means that we can draw a graph of J versus W in what we could call the JW plane. So we could have a JW plane, and we're saying that J is a function of W, which means there's some relationship between J and W. So here I just made an arbitrary shape. This means we can draw a graph of J versus W in the JW plane. For example, this graph. Remember that W is initially randomly assigned. So let's assume that it starts out at some W0, so say here, initially. When we say that we want to change W so that J is reduced, you should realize that we've already discussed the solution to this. It is exactly the method of gradient descent, and it requires knowing the derivative of J, which of course requires the chain rule. So with gradient descent, we can find the way to change W so as to reduce J. That's what gradient descent allows us to do. And the answer is that we change W by dj dw, or actually we allow a little more flexibility than that. We may just say change it. So dw dj might turn out to be, let me say, remember that dw dj is basically the slope. The slope is actually a number. So we can visualize it as the slope of the tangent line, and also as basically we can think of it as a direction, because it's either going to be a positive or a negative number. So it's going to have a direction. So the direction is really going to say, if we're starting here, should we move to the left or should we move to the right, depending on whether the slope is positive or negative. For example, here you can see, of course, that the slope is positive, but the direction we actually want to move is to the left. So a positive slope in general will mean that you want to move to the left. Whereas if we were over here, the slope is negative, and so a negative slope will mean that you want to move to the right. So you can see that visually here. Because of course here, if we're here, we want to move to the right to get to a lower error. But if we're here and we look at the slope, what is the slope? The slope is negative. So a negative slope is going to always mean that you want to move to the right, whereas a positive slope here, this is positive slope, will mean that you want to move to the left. So it's a little bit counterintuitive. But then in addition to the fact that we want to move to the left or the right, when we calculate the derivative, we're getting the slope of the tangent line, and that's a number. And if we're going to use that number to tell us how much to change w by, we could do that. Suppose the slope here is 2. So I could say, okay, I definitely want to move to the left, but I could use the number here to say, okay, let's move to the left by 2 units. Now, depending on the scale here, 2 units, maybe this is only 1 here. So this whole length is just 1. So if I move by 2 units in that case, I'd move way over to here somewhere, I guess way over to here, which is not what I want to do. I only want to move a small amount to the left. So I don't necessarily want to be limited to moving exactly by the derivative. So what we allow for is to move by some amount proportional to the derivative. So suppose, like I said, this whole scale, this was a 1, this W0 is 1 here. So if I move by a slope of 2, if I move by 2, I might move all the way over here, which is obviously not what I want to do. So let's say that we're going to use a rule where we're not going to move by the full amount of, you might say, why should I move by the amount of the derivative? Well, we don't really have any other means to decide how much to move by. So we're going to move by the amount of the derivative or something proportional to the derivative. So we may say, okay, we're not going to move by the amount of the derivative. We're going to move by 1/10 of whatever the derivative is. So that would say, like I said here, if this was 1 and then the derivative was, 2, instead of moving all the way over to 2, we'd go 1/10 of 2, which would mean move just 0.2. So maybe that would be okay. To move 0.2 might just bring me to here, which would be maybe a good place to move to this weight. And then we would do the same thing again. So, and it would depend again, and then the amount we would move and the direction we would move at this point when we're here would again be based on whatever the derivative was here. So that's the basic idea. So anyway, with gradient descent, we can find the way to change w so as to reduce j. And we're going to either change it by exactly dj dw, and then of course the direction, as we said, depends on, in this two-dimensional case, depends on whether dj dw is positive or negative. And again, just to repeat it again, if it's positive, if the slope is positive, that means we're going to move to the left. That means we're going to take W0 and subtract this from it. On the other hand, if it was over here, we said the slope is negative. So in that case, we want to move to the right. So we can subtract the derivative because the derivative is negative. So when you subtract a negative, you get a positive. So you're actually moving to the right. So we can say that we're going to, in this two-dimensional case, we're going to subtract dj dw from the weight to get the new weight. And that's going to be our rule for getting a new weight, for how to update the weight in the right way. If we change W in the right way, we'll know how much improvement we're going to get in J, in the cost, or in the error. Now this is going to tell us how much J will change, but it's not going to tell us, let's say, how much we should increase or decrease W by, or whether we should increase or decrease W in order to reduce J. So this is telling us, well, if we change W by a certain amount, J will change by a certain amount. The question is, do we want to, so we have some idea of how J is going to respond to a change in W. But we also have to decide, should we increase W so that J will decrease? Remember, we want the error to decrease. Or should we decrease W so that the error will decrease? Sorry. And that may ring a bell. And that may ring the bell of gradient descent. That is, we want to go in the direction so that J will decrease. So J is this function that we've been talking about. Remember, we've been talking about being on a mountain. Well, the mountain is the J curve. So the J curve is the thing that we want to get to the bottom of. So we have the J curve, and we want to move in the direction of J decreasing. So we want to get to the valley of the J curve. So we can use gradient descent to tell us where the valley is. In other words, we can use gradient descent to tell us whether we should move east, west, in other words, how we should change things in order to reduce J. And that's where gradient descent comes in. And in order to use gradient descent, we need the gradient, or in other words, we need the derivative. And this is also part of the derivative calculation, and it tells us what it is the derivative calculation. It tells us what the derivative is. So actually, if this is positive, and we go in the direction of whatever direction this tells us to go in, then we will actually be increasing the error, which is just exactly the opposite of what we want to do. So instead of moving in this direction, we move in the opposite of this direction. So now we just have other ways to write the same thing, and this is just exactly the same thing as this, just rewriting J in terms of what it was, rewriting S in terms of what it was, and so on. And then we actually compute the derivative. We do all the work here. It's not very hard, actually. The only thing is here, we use this special symbol, which just stands for a bunch of the terms, that's all. It's not really important, but it's sort of standard to use this. But it's not really important. You could have this just stands for a few of these terms, that's all. So it allows this to be shorter. But anyway, so we calculate this thing, and we get an expression for it in terms of this thing, which is just a bunch of these terms. Like I said, this is really not important, but it's there. Then we also do the same thing for W1. We did it for the closest weight, but we did it for this weight, and we also want to do it for this weight. So we're going to figure out how much we should change this weight by and how much we should change this weight by. So what we're going to do is we're going to change this weight, we're going to change it so that we reduce the error, and that means in order to know what direction to change it and how much to change it, we calculate this. And then we use this. Basically, we take the old weight and we subtract this amount from it, and that's going to be the new weight. So that's actually written here. So the new let's say this one, the new W2 weight is the old W2 weight minus this derivative that we've calculated. And then we're going to do exactly the same. Now this is all the way down on page 270, by the way. And this is the old W1 weight, and then we're going to calculate this. Now this is going to be a longer calculation than this one was, because this is more deeply embedded inside J. In other words, it's more deeply embedded inside J, so it's going to actually be a longer string. It's actually going to be a string of 7 terms instead of this was 5 terms. We didn't bother to count those yet, but this had 5 terms in its calculation of the derivative, and this is actually going to have 7. But anyway, it doesn't matter. So this is one calculation, and we're going to get the new weight by taking the original weight and subtracting. In other words, gradient descent is going to say subtract it, and this is the amount we're going to subtract it by. And the same thing here, gradient descent will say subtract from this. So we're going to start with the old weight and subtract this derivative from it, and that's going to give us a new weight. And now we have the formula for updating the weights. So we're learning from our mistakes. Now it's we just make a little slight difference here. Instead of subtracting this, we decided, well, we don't want to be stuck with having to subtract exactly whatever the size of the gradient is. So let's throw in a little bit more flexibility and just say we're going to subtract a multiple of this. So maybe only a half of this, or maybe only a third of this. So we just don't want to be forced to subtract exactly whatever this turns out to be. Maybe it's better to only subtract half of this when we're updating the weights. So we throw in just an extra constant here and here, and we allow that to be, maybe this is only going to be a half. So then we're only subtracting a half of whatever the gradient is or whatever the derivative is. So we allow that flexibility by throwing in the r there. And that r can be set to different things. If we want to subtract one full gradient, we can have it at 1. If we want it to be a half of a gradient, we can set it to equal a half, and so on. So this process of updating the weights, starting with the original weight and getting a new weight, starting with the So this process of updating the weights, starting with the original weight and getting a new weight, starting with the initial weight and getting a new weight, this is called back propagation, because we're sort of going backwards in the network. First, we're figuring out how to change W2, and then we're figuring out how to change W1. And if we had more layers, we would do it more. So it's called back propagation, and basically it's calculating this derivative and then updating the weight accordingly, and calculating the other derivative and updating the weight accordingly. And as I said, this stuff here is here because it's been used for a long time. They call part of the calculation sigma 1, and they call part of the calculation sigma 2 for the other calculation. So, but you don't need to call it sigma 1 and sigma 2. You could just have this and this. But if you use sigma 1 and sigma 2, then you get that dj d1 is not such a long string, because the long string is embedded in here, and you just get this times one of these terms. Which term was this? D1 is here. The last term is here, and all the other terms are what we call sigma. I'm sorry, delta. This is called delta. All the other terms are delta. So all this stuff is delta, or all this stuff is delta. One of them, we call this one delta 2, I think. We call this one delta 1. So delta 2 is here. So that's all of this, and all we're left with is this one piece here, which is that one piece there. Okay, so that's basically the story. So don't get confused about this delta. Okay, and then we can do all of this with matrices. But anyway, we've covered the basic idea now. So that's the basic idea. We want this because we're going to use those to update the original weights like this. And then what we do is so that was like with the first example, we run it through. we get the error, we update the weight based on the error. Then we take another example and we run it through the network. We get a different error. That'll cause us to update the weight again, probably by a different amount. And we keep doing that. With each example, we can update the weights, and that's called learning. That's what we mean by learning. The weights are getting updated. They're learning from each new example that we throw into the system, and hopefully the predictions get better and better, and they do. Now, if we want to bother to write this in matrix form, we can do that. But that's not the basic idea. The basic idea is what we just said. Now, if we want to get all this into matrix form, we can try and do that, and maybe it'll look nice, and maybe it will make even the R calculate when we're trying to write it in code. Maybe writing it as matrices will make it easier, and certainly easier to look at, because you'll just have, remember we saw that the chain rule, which was kind of messy, could actually be expressed as the product of two matrices. So that's a little bit easier to look at than a long string. So maybe, it'll be easier to read in some way. So that's all we're doing here, is getting it into matrix form. So we do that here and there, and then we start writing the code, and that takes a lot of work. And then we have a function called pred neural network NN single value. So that's the prediction for a single value. We run just one piece of data through one example through. And then, of course, we're going to want to put this into a loop. There could be other ways to do it, but we're going to use a loop and have it run all of the data. Each time we run this, we're going to run it through a loop, but each time we run it, it's going to hopefully improve our network, improve our weights, so that they're better and better at predicting. But anyway, we have this function which does that, and then we want to run it through the entire data set. And then not only that, but then we can actually run it through the entire data set once, but then we can just run it again through the entire data set again. And maybe that will continue to improve the performance, not just on the current data set, which obviously it would. We don't want it just to improve on the current data set, though. We want it to improve in general for new data sets. We can call that the generalization. We want that to improve as well. So we call that epoch. So we run the entire data set through once. That's called the first epoch. We run the entire data set again. That's called the second epoch. So we can easily do that. We just take another loop and run everything through a second loop that repeats everything that happened in the first loop over and over again. So we code first the easy 1-1-1 neural network, where we only have one node in each layer. And then we do the slightly more complex network, and then we do this network. We code it. So that's what a lot of the chapter is about. And it's also about putting it into matrix form. We have to write code, of course, for updating the weights. And then here we try it on some new data. We test out our code on some new data, and we see how it does. And we go through one epoch, and then I think the first epoch is here, and we have the error. Then we run it through a second epoch, and we get error, and we see that the error is reduced. And then we run it through another epoch, and the error is reduced further. And we keep running it through increased epochs, and we see that the cost is being reduced. And in the process, we learn a lot about the programming. Now, we mentioned up earlier that we may not want to increase or decrease the weight by a full derivative. And so we threw in an extra factor of R, factor of proportionality, which we could set to 1, but we could also set to 1/2. That R is called the learning rate. And we have other things that we can adjust in the network And those altogether, those things are called hyperparameters. And so at the end of this chapter, we've created a neural network with 3 layers. And in the next chapter, we're going to use classes from R to make the code more elegant. So we actually create a neural network, we test it out on some real data, and we get some good performance on that real data.